A giant stone block weighs as much as 50 jet planes. Ancient builders moved it anyway. This video reveals how they did it by investigating the very places the stone was born and the tools they left behind. You will gain a complete picture of ancient ingenuity, one that transforms silent ruins into stories of brilliant engineering. How did workers in a quarry shape granite harder than steel using what we call simple tools? Why do some stone surfaces bear marks that look like they were made by machines? We will follow the evidence from deep trenches in Egyptian rock to the staggering megaliths of Lebanon. By the end, you will not look at a pyramid or an Inca wall the same way again. What does it truly mean to leave a mark on the world that lasts for thousands of years? Run your fingers along the stones of Machu Picchu. You feel no ridge, no bump, no gap. The fit is so impossibly tight that modern tools cannot slip into the seam. This is not just good masonry. It feels like magic, a silent taunt from the past. And it presents us with a profound and humbling paradox. According to the established timeline, the builders of these wonders had only simple tools: copper chisels, stone hammers, abrasive sand. Theoretically, these should have been enough, given enough time and labor. Yet when you stand before a pyramid's casing stone or an Inca junction cut with geometric perfection, a quiet voice whispers that the theory feels incomplete. The scale is too vast, the precision too consistent, the results too flawless. Archaeologist Mark Lehner, who has spent decades at Giza, speaks of this gap. He describes an operation of industrial magnitude, one that seems to defy the straightforward story of men with basic copper tools patiently pecking away at granite harder than steel. This initial bewilderment is where every true investigation begins. It is the moment you realize the textbook explanation cannot fully account for the artifact in front of you. That feeling, that gap between what we think we know and what the stone itself declares, is the foundation of our entire mystery. It forces us to stop making assumptions and start following the evidence. And the evidence does not begin at the finished temple. It begins miles away, in the raw, scarred landscapes where the journey of these megaliths truly started. To understand the end product, we must first visit the birthplace. Deep in the granite heart of Aswan, a monument sleeps within the earth. The unfinished obelisk is not a ruin. It is a fossilized moment of work in progress, a 1,100-ton lesson carved directly into the living rock. Here, the stone itself is the primary witness, and its testimony is remarkably clear. The method on display is one of subtraction. To free this colossal needle, workers did not attack it from above. Instead, they carved a series of deep, narrow trenches completely surrounding its intended shape, channeling down through the granite to isolate it from the bedrock. This trenching process is visible today as a stark negative space, a deep gutter in the stone. But how do you carve a trench in granite, a stone so hard it sparks against steel? The answer lies in the simplest of tools and a profound understanding of material. Workers used hand-held pounders made of dolerite, a stone even harder than the granite itself. For months, perhaps years, teams would have methodically pulverized the granite along a marked line, turning solid rock into a fine dust that could be swept away, millimeter by agonizing millimeter. The sound must have been deafening, a constant, rhythmic percussion echoing through the quarry, a testament to sheer human endurance. Yet within these trenches, archaeologists notice another clue, a series of carefully cut slots running in neat rows. These are the beds for wooden wedges. The process was ingenious. Once the trench was deep enough, workers would insert dry wooden blocks into these slots, then soak them with water. As the wood expanded with tremendous, relentless force, it would create a controlled fracture along the base of the obelisk, finally prying it free from its ancient cradle. This snapshot reveals a system that worked, a symphony of simple physics and immense labor, but it also frames a haunting question. This obelisk was never finished. A flaw in the stone caused it to crack, halting the project forever. Looking at the scale of the trenches, the sheer volume of granite that had to be pulverized and removed, one cannot help but wonder. For projects of this magnitude, spanning generations, was this the only way? The evidence from Aswan shows us a method that is comprehensible, but the logistical weight of it is staggering. It compels us to look elsewhere, to sites where the stone bears different kinds of marks that tell a different, and perhaps even more puzzling, story. But the quarry at Aswan is not the only place where the earth holds a giant in waiting. Travel to the Bekaa Valley in Lebanon, and you will find a different kind of lesson carved in limestone. Here rests the stone of the pregnant woman, a single block estimated to weigh over 1,000 tons. To put that in perspective, it is roughly the weight of 250 full-grown elephants. This monolith was cut from the earth but never moved to its intended home, leaving it as a permanent resident of the quarry, a frozen ambition of staggering scale. The platform at Baalbek, where this stone was meant to go, is already composed of blocks weighing 300 to 400 tons each. They were moved and set in place. But this 1,000-ton Leviathan, represents a leap into another realm of engineering audacity. Why attempt it? What possible purpose could justify the monumental risk and labor? The block itself offers clues. French architect and archaeologist Jean-Pierre Adam studied its base meticulously. He noted something fascinating. The underside of the block is not flat. It was carefully undercut, creating a series of precise pockets and levering points. This was not an accident of extraction. It was the first step in a carefully planned moving operation. The proposed technique begins similarly to Aswan. Workers would have carved a deep trench around the block, isolating it, but then the real challenge. How do you persuade a small mountain to budge? The theory involves a symphony of simple machines. First, a bed of wooden rollers or a lubricated clay track would be prepared. Then, using massive wooden levers inserted into those prepared pockets at the base, teams of hundreds could begin the initial, agonizing lift, just enough to slip rolling logs underneath. From there, with ropes and manpower, the block could be inched forward. Some researchers even suggest the use of a massive counterweight crane, a Roman device called a polyspaston, to help with the initial pivot onto its rolling cradle. The local limestone, while more workable than granite, presents its own paradox. It is softer to shape, but its immense weight makes the physics of movement almost unbelievable. This forces us to consider the true marvel not as the tool, but as the organization, coordinating hundreds of workers to pull in unison, to place levers and rollers in a precise sequence, to maintain a perfectly level track for miles. This is a feat of social engineering as much as physical engineering. When you stand before the smaller, exquisitely finished blocks of the Baalbek temple, you see the result of such coordination. Their perfect joints and smooth faces speak of a final, refined stage of work. But the pregnant stone asks a more primal question. It represents the moment before refinement, the raw, terrifying moment of ambition where a culture looked at a mountain and said, "We will take a piece of it and we will make it fly." The sheer scale of that intent forces us to look closer at the final stage, the moment of perfect finish. How did they take these rough, quarried giants and transform them into the seamless, polished marvels that leave us breathless? That answer lies not in the quarry, but in the subtle marks left on the dressed stone itself. The quiet hum of a modern diamond saw slicing through granite is a sound of pure efficiency. It feels like a cheat code against stone. Now, strip away the electricity, the precision motors, the industrial diamonds. What are you left with? The common answer is a copper chisel, a simple tool for a simple time. But this is where our mystery deepens, because the ancient toolbox was far from simple. It was a curated collection of material science, each tool a specialized answer to a specific, brutal question. Copper was indeed present, but it was rarely used alone against hard stone like granite. An experimental archaeologist named Denai Stocks spent years testing these methods. He demonstrated that a copper alloy chisel, when used not to cut but to grind, became remarkably effective. The secret was the abrasive. Workers would pour a slurry of wet sand, often containing extremely hard quartz or corundum particles, onto a granite surface. Then, using a copper saw or chisel, they would patiently drag the tool back and forth, pressing the abrasive grains into the stone. The copper itself was too soft to scratch the granite, but it acted as a carrier, embedding the harder sand particles which did the actual cutting. It was a process of relentless, slow-motion abrasion, turning solid rock into a paste that could be washed away. This explains the smooth, almost polished channels found in certain cuts. But what about drilling a hole? The evidence is preserved in famous granite core samples, like one from Giza now in a British museum. The core shows clear, concentric grooves spiraling down its length. This is the signature of a tubular drill. Picture a hollow tube, perhaps made of copper or even a sturdy reed, attached to a bow. The end of the tube would be loaded with the same abrasive slurry. As a worker sawed the bow back and forth, spinning the tube, the abrasive would grind a circular groove into the granite. Over hours, the tube would sink deeper, leaving behind a solid stone core inside it. This was not a punch, it was a precise, rotary grinding machine powered by human hands. The toolbox expands further from there. There were dolerite-pounding stones for the brute force work of quarrying, as we saw at Aswan. There were wooden wedges swollen with water to split stone along natural lines. There were picks made of hardened bone or antler for detailed work in softer limestone. And there may have been saws, not with teeth but with straight blades of copper or even stone, again used with abrasive slurries to slice through blocks. This cumulative knowledge represents a profound technological ecosystem. It was a system that worked, one we can replicate and understand. Yet, when we return to the stones themselves, to certain specific marks and achievements, a quiet doubt can linger. For every smooth, abraded surface, there is another with a cut that seems too clean, too deep, or executed on a scale that defies the slow, grinding logic of sand and copper. The toolbox we have uncovered is comprehensive, but was it universally applied? Or does the stone itself preserve clues to techniques we have yet to fully rediscover? To answer that, we must move from the tools to the traces they left, examining the most enigmatic marks of all. Granite does not lie. Its crystalline structure records every interaction with a brutal honesty. In the Cairo Museum rests a sarcophagus lid, a single slab of red granite polished to a mirror finish, but it is the underside that holds the secret. Carved into the stone are a series of perfect concentric grooves, spiraling out from a central point with a regularity that is almost hypnotic. To a modern machinist, the pattern is unmistakable. It looks exactly like the mark left by a large horizontal lathe where a cutting tool was fed steadily across a spinning block. The precision is mathematical, the symmetry flawless. This is not the rough, pecked surface of a dolerite pounder or the gritty, abraded channel from a copper saw and sand. This is something else entirely. It is one of many such anomalies, a ghost in the stone that whispers of a process we thought was invented millennia later. Engineer and researcher Christopher Dunn has spent decades cataloging these enigmatic marks. Applying a machinist's eye, he measures flatness, parallel lines, and internal corner angles that approach true 90 degrees, features exceptionally difficult to achieve with freehand tools. He points to blocks at Giza where the surfaces are not just flat, but planar across vast areas, as if milled by a giant, guided blade. Then there are the scooped-out depressions in soft stone, like those found in some Egyptian temples, that curve with a smooth, consistent radius as if made by a rotating tool. And perhaps most puzzling of all are the perfect spherical cavities drilled into hard stone at sites like the Osirian, holes that imply a drill bit that not only rotated but could also pivot on a fixed point, like a modern ball mill. The theories proposed to explain these marks are as ingenious as the marks themselves. One suggests the use of large, bow-driven horizontal lathes. Imagine a massive granite block mounted on a central pivot, turned slowly by teams pulling on ropes wound around its axis. A fixed cutting arm laden with an abrasive slurry could then be gradually fed into the spinning stone, creating those concentric grooves. Another idea involves guided straight edges for saws. Instead of a worker freely dragging a copper blade, the blade would be mounted within a rigid wooden frame that slides along a track, ensuring a perfectly straight, unwavering cut. There is even speculation about the use of abrasive cords, like a giant, endless loop of string embedded with sand, that could be pulled back and forth to saw through stone, creating incredibly narrow, parallel curves. This conversation reaches a crescendo at a site like Puma, Punku in Bolivia. Here, andesite blocks are not merely cut, they are engineered with a complexity that stuns the observer. They feature precise, interlocking channels, razor-sharp inner corners, and repeating geometric patterns of such exactness that they look prefabricated. The stone itself is notoriously hard, a volcanic rock that challenges modern tools. The technical skill implied here seems to leapfrog over the basic quarrying methods we understand. It pushes us to ask a fundamental and humbling question. Are we looking at the absolute zenith of human hand skill, a level of artisan mastery so refined it appears mechanical to our modern eyes? Or do these stones preserve faint echoes of a different approach to working stone, a methodology or technology that has not survived in the toolkits we have found? This is not a call for fantastical explanations, but a plea for open-minded investigation. The marks are real, their precision is measurable. The pursuit of understanding them leads us away from speculation and directly into the hard science of the material itself. To decode what the stone is telling us, we must learn to listen in its own language, the language of chemistry, physics, and microscopic wear. Granite holds its secrets at a scale invisible to the naked eye. To move beyond the marks we can see and into the realm of what truly happened, we must shrink our perspective down to the microscopic world within the stone itself. This is the domain of petrography, a forensic science for rocks. Think of it as listening to the stone's own testimony, spoken in the language of its crystal structure. Materials scientists take incredibly thin slices of stone, samples no thicker than a human hair, and place them under powerful microscopes. What they see there is a detailed record of violence and precision, a permanent log of every force that ever touched that surface. The key witnesses are the mineral grains, particularly quartz, which is harder than steel. When a stone is struck by a pounding tool like a dolerite maul, the energy travels through the crystal lattice like a shockwave. Under magnification, this reveals a zone of utter devastation. The quartz crystals are not just cracked, they are brutally shattered into a fine, powdery dust, with fractures radiating chaotically in all directions. It is a signature of blunt, overwhelming force. Now contrast that with the evidence left by a grinding or slicing action. When an abrasive slurry of sand is dragged across granite by a copper tool, the effect is entirely different. The hard quartz grains in the slurry act like countless microscopic blades, shearing across the surface of the stationary quartz crystals in the bedrock. This process, called abrasion, creates a polished, almost smeared appearance on the crystal faces. The fractures are shallow, parallel, and orderly, like the fine scratches on a well-used piece of glass. This scientific lens transforms speculation into data. it allows researchers to do something remarkable, to distinguish not just between tools but between intentions. A shattered crystal layer means this spot was hit repeatedly and with great force. A polished, scratched layer means this spot was ground patiently and with guided motion. The process of obtaining these samples is handled with extreme care, often taking minute slivers from existing fractures or unseen areas to preserve the integrity of the monument. It is archaeology at its most delicate, respecting the past while seeking its truths. This methodology has been applied to artifacts around the world, offering stunning clarity. For instance, analysis of the colossal basalt heads created by the Olmec civilization in ancient Mexico revealed a clear petrographic story. The stone showed the hallmarks of abrasion, but with a specific twist. The consistent, polished wear patterns indicated the use of hard stone tools combined with water and an abrasive like sand, a meticulous process that could shape even the toughest volcanic rock into those iconic, serene faces over countless hours. This microscopic evidence does more than confirm techniques. It reframes our entire view of ancient work sites. A quarry was not just a place where rocks were broken. It was a complex industrial landscape, a factory floor where different stations employed different technologies. One area might show the petrographic signature of heavy pounding for primary block removal. Another area, perhaps a finishing station, might reveal the fine abrasion marks of precise shaping. The stone's microstructure allows us to map this workflow, to see the logical progression from raw brute force to refined artistry. It gives us a ledger of labor written in crystal. With this concrete evidence in hand, we can finally return to the grandest sites not with wonder alone, but with a new, evidence-based framework. We can look at a perfectly smooth pyramid casing stone or a seamless Inca joint and ask a more informed question. What sequence of forces of pounding, grinding, and polishing could possibly lead to such an impossible finish? The microscopic world has given us the rules of the game. Now we must apply them to the most extreme examples, to the stones that still seem to defy every logical expectation. A finished block resting at the temple site tells only half the story. To grasp the full scope of ancient ambition, you must look at the place it began, not as a scar on the landscape, but as a living, breathing machine. From the air, a major quarry reveals itself as a feat of logistics as brilliant as any monument. Industrial archaeologists now map these sites like the blueprints of a factory, revealing an integrated system of extraction, processing, and transport. At the famed limestone quarries of Tura in Egypt, the evidence is etched into the ground. You can still trace the main haul road, a wide, smoothed highway leading directly to the Nile. Along its edges are the ruins of loading docks where blocks were transferred to barges. Nearby, scattered piles of chert nodules, the waste product from sharpening countless copper tools, mark the locations of permanent sharpening stations. This was not a chaotic dig site. It was a precisely orchestrated industrial landscape. The workflow began long before the first hammer fell. Prospectors would test the bedrock for hidden flaws. Then overseers marked the quarry face in a precise grid, planning the extraction sequence like a three-dimensional puzzle. Workers did not simply hack out stone at random. They cut in a stair-step pattern, removing blocks from the top down in a controlled sequence to maintain the stability of the quarry walls and ensure the quality of the material below. This methodical removal created the dramatic, terraced cliffs we see today. Each massive block, once freed, was not finished here. It was only rough-shaped, its weight reduced just enough for transport, becoming a blank canvas for the artisans at the building site. The social organization mirrored the physical layout. A strict hierarchy operated within the dust and din. Skilled master cutters who understood the stone's grain and temperament directed the primary cutting. Teams of trained laborers operated the levers and ropes, A larger force of unskilled workers handled the brute transport and provided the endless human power. This entire city of labor required constant provisioning. Archaeologists find the remains of bakeries, water storage cisterns, and dormitories at larger quarry sites. Feeding and housing thousands of workers in a remote, arid location was an achievement of administration equal to moving the stone itself. The Romans later perfected this model into a standardized industry. Their lapicidinae or stone quarries produced blocks in predetermined sizes. Think of it as ancient mass production. A standard-sized block could be loaded onto a standard wagon, pulled by a standard team of oxen, and slotted into a building project with minimal additional cutting. This efficiency of scale turned construction into an assembly process. When you stand before a Roman aqueduct or theater, you are seeing the end product of this relentless, organized system. The true genius, then, lies in the seamless connection between these two worlds. The quarry was the engine of raw material. The temple was the gallery of final form. The invisible link between them, the miles of haul roads and river journeys, represents a triumph of planning that made the impossible routine. It forces us to ask a final, pivotal question. With this engine of production now understood, with its blocks delivered, what happened at the building site to transform this raw potential into the seamless, gravity-defying architecture that has captivated humanity for millennia? A rough block fresh from the quarry is a brute of a thing, all jagged edges and uneven weight. Its journey from that state to a perfectly smooth, geometrically precise building stone is where the true artistry begins. This stage is called dressing, and it is a world away from the brute force of quarrying. It is a patient, meticulous dialogue between the craftsman and the material. Modern experimental stonemasons like Roger Hopkins have spent lifetimes relearning this lost conversation. By using replicas of ancient tools on fresh stone, they reveal a logical, step-by-step sequence that turns chaos into order. The process always begins with the point chisel, a tool with a sharp, narrow tip. The mason uses it not to slice, but to peck, striking controlled blows to knock off the largest protrusions and bring the block down to its general shape. The stone surface after this stage looks pockmarked like the skin of an orange. Next comes the flat chisel or drove. With a broader edge, the mason works across the pitted surface, shearing off the high points created by the point work. Each pass makes the stone a little smoother, a little more even. You can almost hear the change in sound, from a sharp tink to a softer shush as the contact area increases. Finally, for the finest work, the mason might employ a drag, a flat piece of metal with a toothed edge, or simply a rubbing stone, used with water and an abrasive slurry of fine sand or even crushed emery. These tools grind the last microscopic imperfections away, leaving a surface that is plainer and smooth to the touch. The evidence for this exact sequence is written in the stone waste of ancient sites. Archaeologists find discarded blocks and fragments bearing these distinct tool marks, frozen in various stages of completion. They are snapshots of the workflow, showing us that the journey was never a single leap, but a deliberate, practiced climb toward perfection. Nowhere is the culmination of this climb more breathtaking than in the lost casing of the Great Pyramid. These were not simple blocks. They were immense slabs of fine white Chora limestone, each one dressed to fit not just against its neighbors, but to form part of a vast, sloping plain that had to maintain a perfect, consistent angle across the entire face of the structure. Think of trying to hand sand a wooden board the size of a football field, ensuring that not a single spot dips or rises beyond a fraction of an inch. The casing stones that remain at the pyramid's base show us they achieved exactly that. The joints between them are so precise that the gap is often less than the thickness of a credit card. This level of consistency across such a scale forces a profound question. A single artisan can dress a single stone beautifully. But how did hundreds of artisans working on thousands of stones over decades ensure that every single piece conformed to the same master plan? How did they communicate angles and flatness without laser levels or digital protractors? The answer lies not in the tools that shaped the stone, but in the invisible systems that guided the hands that held them. The final, polished stone is a testament to the hand, but the wall it fits into is a testament to the mind. Before a single chisel touched the quarry, before the first rope was laid for hauling, the entire endeavor existed as a perfect geometric idea in the mind of a master builder. This intellectual framework, this invisible architecture of measurement and mathematics, is what transformed chaotic piles of rock into structures that stand true after thousands of years. The true tool was not the copper saw, but the system. Imagine a master builder on a vast, empty plateau, tasked with laying out the foundation for a pyramid. His toolkit is startlingly simple: a length of rope knotted at precise intervals, a wooden rod with a weighted string, a plumb bob, a shallow trough of water. Yet with these humble instruments, he could inscribe perfect squares, align walls to the cardinal directions, and ensure that every course of stone would be perfectly level. The key was the application of a standardized unit of measure. The ancient Egyptians used the royal cubit, a length derived from the forearm, standardized across the kingdom and represented by physical rods of wood or stone. Every dimension of a sacred building was a multiple or fraction of this unit, creating a harmony of proportions that was both practical and symbolic. To establish a right angle, they employed the timeless principle of the 3-4-5 triangle. By marking a chord with 12 equally spaced knots, a worker could stretch it into a triangle with sides of 3, 4, and 5 units. The angle between the 3 and 4 unit sides is a perfect 90 degrees. This simple trick, known for millennia, allowed for the precise squaring of massive foundations. For leveling, the water level was revolutionary in its simplicity. Water, in a long, straight trough or even in connected vessels, always finds a perfectly horizontal plane. By sighting across the still surface, builders could transfer this level reference across any distance, ensuring that the first layer of stones was perfectly flat, a critical prerequisite for everything built upon it. And for aligning structures to the stars, they used instruments like the Merkit, a sighting tool with a plumb line that allowed priests to track the transit of specific stars, locking the axis of a temple or pyramid to the cosmos itself. The evidence for this meticulous planning is etched into the stones and the sites. On quarry floors, archaeologists have found geometric patterns scratched into the bedrock, full-scale templates used to outline complex blocks before they were cut. In Roman construction, the consistent dimensions of bricks and blocks speak of a standardized, modular system that allowed for mass production and assembly. The most staggering example of this intellectual mastery remains the Great Pyramid of Giza. Its base is a near-perfect square, with sides aligned to the cardinal directions with an error of less than a fraction of a degree. Achieving this required not just astronomical observation over many nights, but an unwavering geometric discipline maintained across a construction site larger than a modern city block. This reveals the core truth: the method was never just about physical force. It was a seamless fusion of muscle and mind, of labor and logic. The stones were shaped by tools, but the monument was shaped by mathematics. This profound understanding of geometry and physics raises a final, fascinating possibility. If they could command hard stone with such precision, what could they achieve with materials that were, by their very nature, more forgiving? What if the ultimate secret was not about cutting stone apart, but about bringing it together in an entirely different way? Granite yields to the relentless grind of sand and copper, but what if there was another way? What if the ancient artisans possessed a kind of alchemy, a knowledge that could temporarily persuade stone to soften its defiance? beyond the physical tools of hammer and wedge, there exists a persistent undercurrent of speculation about forgotten methods, whispers of chemical brews and controlled fire that could make hard rock briefly pliable. This is the realm of the soft method, a controversial yet fascinating frontier in our investigation. To understand it, we must temporarily set aside the stone itself and listen to the stories passed down through time. From the forests of South America to the islands of the Pacific, ethnographic records collected by early anthropologists speak of indigenous stoneworkers using plant extracts. These were not mere lubricants, but solutions described as capable of softening rock, allowing it to be shaped almost like wet clay before it re-hardened. A specific vine or tree bark would be soaked, producing a liquid that was then applied to the stone surface. The descriptions are compelling, but they reside in a gray area between oral tradition and verifiable technique. Modern chemistry offers a skeptical but not entirely dismissive lens. Material scientists note that most rocks, especially silicates like granite, are inert to organic compounds. A plant juice, no matter how potent, is unlikely to alter the fundamental crystalline structure of quartz. However, the story shifts when we consider a different kind of stone, limestone. Limestone is primarily calcium carbonate, and it reacts with acids. Here, the speculative meets the plausible. A weak acid, such as acetic acid from fermented fruit or vinegar, could indeed react with a limestone surface. It wouldn't melt the block, but it could create a softened, paste-like layer on the very top. An artisan could then scrape this paste away, revealing fresh stone underneath, and repeat the process. It would be a form of chemical abrasion, potentially less labor-intensive than constant pounding. This might explain certain finely detailed carvings in soft stone that lack clear tool marks. Yet for every possible explanation, there is a myth that crumbles under scrutiny. One of the most enduring is the theory of thermal shock, often depicted in dramatic recreations. The idea is simple and visually striking. Workers would light a large fire directly against a granite cliff face, heating the stone intensely. Then, just as it reached peak temperature, they would douse it with cold water. The sudden contraction, the theory goes, would cause the rock to fracture and spall off in large sheets. While thermal shock is a real geological phenomenon, practical experiments by engineers have largely debunked its usefulness as a precise quarrying tool. The process is wildly uncontrollable. It creates a zone of severely weakened, micro-fractured stone that is useless for fine construction. The fractures are chaotic, running deep into the bedrock and compromising the integrity of any block you hope to extract. It is the equivalent of using an explosion to carve a statue. The result is damage, not design. This tension between compelling anecdote and hard science reaches a peak with one of the most tantalizing clues from Egypt itself. A few fragmentary papyri, translated by specialists, contain cryptic references to a substance or process described as the stone that melts. The phrase ignites the imagination. Was this a technical term for a quarrying method, a metaphor for the transformative power of craftsmanship, or a literal description of a lost technique? Without a detailed recipe or archaeological evidence of its use, it remains an enigmatic footnote, a ghost in the textual record. This foray to the edges of known science is not about proving the impossible. It is about practicing a disciplined, open-minded skepticism. It encourages us to separate romantic legend from testable hypothesis, while acknowledging that the full breadth of ancient material knowledge may not have survived in the toolkits we've unearthed. The true lesson here is about the human impulse to seek efficiency. If a plant extract could save a month of labor, it would have been a treasured secret. If fire could be tamed to aid splitting, it would have been attempted. Our journey has now armed us with a complete picture of the stone's origin, from the organized chaos of the quarry floor to the refined logic of the dressing yard, and even to the speculative frontiers of material science. With the block finally shaped, a final, monumental challenge remains, one that requires leaving the quarry behind entirely. How do you move a small mountain across miles of rugged earth? The ground itself would have trembled. Picture a procession of 100 men, muscles straining against thick ropes, inching a wooden sledge bearing a 200-ton block of limestone across the desert. This was not a rare spectacle. It was the daily, grinding reality of moving a mountain one piece at a time. The quarry produced the raw material, but the true test of ancient ingenuity was the journey between. This phase demanded a different kind of genius, one that married simple physics with staggering logistical coordination. Transport archaeologists, by studying the very earth around quarries, have pieced together this lost art of megalithic motion. The evidence is often subtle: a preserved trackway of compacted earth and stone, parallel grooves worn into bedrock from countless sled runners, or the remains of a massive, purpose-built causeway leading straight to a river. The methods were elegantly straightforward in concept but breathtaking in execution. For overland transport, the sledge was king. A massive block would be levered onto a heavy wooden sled. The path ahead was not left to chance. Workers would prepare a track, sometimes laying down wooden rails or a bed of lubricated clay. The most famous lubricant, depicted in Egyptian tomb paintings, was water, poured before the sled to reduce friction dramatically. Experiments have shown that on a slick, muddy track, the force required to pull a massive weight can drop by half or more. For the initial movement or for precise positioning, levering was critical. Using long, stout wooden levers inserted into prepared slots, teams could rock a block incrementally forward or pivot it onto its transport cradle. The true scale of this operation is written in the landscape. At the bent pyramid at Dosha, a vast raised causeway of stone and rubble still stretches from the Nile Valley toward the monument, a permanent highway for eternity. Tomb illustrations from Deir el-Medina give us the numbers, showing teams of dozens, sometimes over 170 men, hauling a colossal statue, with a foreman standing on the knees of the figure clapping rhythm to coordinate the pull. This was engineering conducted as a form of music, a rhythm of collective effort. For cultures blessed with waterways, the challenge transformed. In Egypt, the Nile was the nation's conveyor belt. Blocks from quarries like Aswan were loaded onto enormous, purpose-built barges during the annual flood, when the river's higher water level allowed these heavily laden vessels to float. They would then drift north with the current, a journey of hundreds of miles with minimal effort. A stunning example of these principles, though from a much later era, is the transport of the thunder stone in 18th century Russia. This 800-ton granite monolith, destined to become the pedestal for the bronze horseman statue in St. Petersburg, was moved overland for nearly 4 miles. Engineers employed a brilliant system, placing the stone on a huge metal sledge that rolled over a track of synchronized bronze spheres, which themselves rolled in grooved wooden rails. It took 400 men 9 months, using capstans and levers, to complete the journey, a project that directly echoes the methods and immense patience of the ancient world. This final link in the chain, from quarry to river, from river to causeway, from causeway to foundation, completes our understanding. It reveals a process not of mystery, but of magnificent, coordinated effort. Each culture adapted these principles to its own environment, from the rope and log systems of the Inca in their mountainous terrain to the river barge networks of Mesopotamia. The stone's journey was a symphony of simple machines, guided by a master conductor's understanding of physics and human potential. With the block finally at the building site, positioned with similar levering and ramp techniques, the final act could begin. The act of locking these giants together into a form meant to defy time itself. The final, assembled wall is where philosophy becomes visible in stone. At Sacsayhuaman, high in the Peruvian Andes, the architecture feels alive. giant blocks of hard diorite and limestone are locked together in a sprawling, three-dimensional jigsaw puzzle, their edges meeting in a network of zigzagging seams. No two stones are the same. Each is a unique, irregular polygon, its neighbors shaped perfectly to receive it. This is polygonal masonry, and it stands in stark contrast to the serene, horizontal order of an Egyptian pyramid, built from thousands of identical, rectangular ashlar blocks stacked in neat, predictable courses. These two iconic styles represent not just different aesthetics, but fundamentally different technological philosophies, born from their environment and their purpose. The Inca did not build on flat desert plains. They built on mountain ridges, on seismic fault lines that tremble with tectonic energy. Their solution was not to fight the Earth's movement, but to design with it. The irregular, interlocking joints of a polygonal wall allow the entire structure to flex and settle during an earthquake without collapsing. It is architecture as a shock absorber. To achieve this, the Inca developed a technique that was profoundly tactile and iterative. Archaeologist Jean-Pierre Protzen spent years studying their methods. He describes a process he calls cut and try. Imagine two massive stones already roughly shaped. Workers would position one above the other, then lower it repeatedly, grinding it down onto its neighbor. Wherever a high point made contact, it would be marked, then painstakingly abraded away with stone hammers and bronze tools. This was not about creating a perfect block on a workbench. It was about creating a perfect marriage between two specific stones, a dialogue conducted through patient, physical trial and error. The result is that legendary knife-blade tight fit achieved without a single drop of mortar. The stone itself was the fastener. Now shift continents and climates. In the stable, flat expanse of the Egyptian desert, the challenge was different. Here, the goal was not seismic resilience, but celestial alignment and eternal stability. The philosophy favored pre-planning and standardization. In the royal quarries, blocks were cut to a common dimension, the royal cubit. They were dressed on site to near perfection before they ever left the ground. This system of ashlar masonry relied on a perfectly level foundation, achieved with water-filled trenches, and the assembly was a process of stacking identical units like bricks. The tools reflected the material. Egypt often worked with relatively softer limestone and sandstone, which could be efficiently shaped with copper chisels and abrasive sand. The Inca, facing harder volcanic rock, relied more on durable stone pounders and the grinding power of abrasives. This comparison dissolves the myth of a single ancient method. Instead, it reveals a brilliant spectrum of adaptation. One culture developed a flexible, organic system for a living, moving landscape. The other perfected a rigid, geometric system for a static, eternal plane. Both achieved a level of precision that humbles modern observers, yet they arrived there by listening to the demands of their stone and their world. This understanding of diverse genius prepares us to look further back, to sites where the stonework presents a different kind of puzzle altogether, one that seems to blend these philosophies in ways that continue to challenge explanation. 12,000 years ago, a group of people looked at a limestone ridge in southeastern Turkey and saw something more than a hill. They saw a temple. At Göbekli Tepe, the timeline of monumental stonework is shattered. This site predates Stonehenge by 6,000 years and the pyramids of Giza by 7,000. It was built not by a settled agricultural society with a king and a bureaucracy, but by communities of hunter-gatherers. The evidence they left behind forces a complete rethinking of what we believe about technological progress and human collaboration. The central marvels are the great T-shaped pillars, some standing over 16 feet tall and weighing more than 20 tons. Each was quarried, shaped, moved, and erected using nothing more than stone tools, human muscle, and a shared vision. The lead archaeologist, Klaus Schmidt, spent decades piecing together their methods. The the local limestone, while softer than granite, still presented a formidable challenge. The toolkit was elemental. Flint and obsidian, stones that fracture to a razor-sharp edge, were the cutting blades of this revolution. For the heavy work of shaping the rough pillars, workers used hand-held hammerstones, pecking away at the surface in a relentless rhythm to gradually define the form. For smoothing, they employed abrasive sands, grinding the surfaces with slabs of sandstone to achieve a more uniform finish. But the true testament to their skill is not in the pillars' size, but in their artistry. The surfaces are alive with detailed bas-relief carvings of animals, foxes, boars, cranes, and scorpions, rendered with a flowing, confident line. This fine detail work was achieved with delicate flint berens, a kind of stone engraving tool used to incise the limestone with precision. To create these carvings, an artisan would have needed not just a steady hand, but a mind capable of holding a complex image and transferring it directly onto the stone, a process requiring immense planning and confidence. The quarry itself lies just a few hundred meters from the enclosures. Here, archaeologists found the empty sockets in the bedrock where pillars were extracted. The method was a scaled-down version of what we would later see in Egypt. Workers would have carved channels around a pillar using hammerstones, then likely used wooden levers and ropes to free it. Transporting a 20-ton pillar without wheels, without draft animals, across even a short distance of broken ground is a staggering feat. The most plausible theory involves a combination of log rollers, rope sledges, and the coordinated labor of dozens, if not hundreds, of people. This is the profound insight of Göbekli Tepe. The technology is comprehensible, but the social achievement is breathtaking. It means that thousands of years before cities, before writing, before metal, humans were capable of organizing themselves around a common, non-utilitarian goal. They gathered, they planned, they fed a large workforce, and they executed a project that would outlast them by hundreds of generations. This site challenges the linear model that says complex society must come first, followed by monumental architecture. At Göbekli Tepe, it seems the architecture may have come first, serving as the social glue that brought scattered bands together, and perhaps even planted the seeds for the settled societies that followed. It proves that the drive to shape stone, to leave a permanent mark, is not a product of civilization. It is one of the very forces that created it. The true technology was not in the tools, but in the minds and hands that wielded them. Behind every perfect seam and every soaring wall stood an individual whose skill was a lifetime in the making, a living library of tactile knowledge passed from one generation to the next. This human element, the society of the stonecutter, is the final, vital layer to our mystery. To understand it, we must shift our focus from the quarry floor to the community, from the mark on the stone to the calloused hand that made it. The transmission of such a complex craft required a social structure as deliberate as the architecture it produced. In cultures around the world, from the Andes to the Nile, this took the form of master-apprentice relationships, often organized into guild-like brotherhoods. Studies of traditional stonemason communities in India, where families have worked stone for generations, offer a powerful analogy. Here, a young apprentice does not begin with theory. He begins by watching, by fetching water and abrasive sand, by feeling the different hammers. His education is a slow immersion, a building of muscle memory, and an intuitive sense for the stone's grain and fracture points. Complex geometry is taught through physical templates and rhythmic chants, a fusion of oral tradition and hands-on practice. This method of knowledge transfer, safeguarded within families or closed guilds, was both its strength and its fragility. The knowledge resided not in books but in people. The social standing of these artisans varied dramatically across cultures and directly influenced their work. In some contexts, they were highly respected specialists, the master builders of Egypt. Men like the famed architect Imhotep achieved near legendary status. Tomb paintings in places like Thebes vividly depict sculptors and draftsmen at work, their tools and postures rendered with care, indicating a valued profession. Physical anthropology adds another dimension to this story. Studies of skeletal remains from ancient workers' cemeteries reveal the literal imprint of their labor. Archaeologists find distinct patterns of bone development and stress, such as enlarged shoulder and arm bones, arthritis in the elbows and wrists, and spinal compression, all consistent with a lifetime of lifting, hammering, and carving. These are not just anonymous laborers. They are individuals whose bodies became a testament to their craft. In other societies, particularly those reliant on large-scale, state-driven projects, many workers were conscripted or enslaved. Yet even here, evidence suggests a hierarchy of skill. Overseers and master craftsmen directed teams of less skilled laborers, creating a system where critical knowledge was concentrated in a few, ensuring quality and control. The Romans institutionalized this idea brilliantly with their collegium fabrum, the builders' guilds. These were professional associations that set standards, trained members, and spread a unified construction methodology across the vast empire. A mason from Gaul could understand the principles used in a workshop in Syria because the knowledge was codified within the guild system. This raises a profound and haunting question about the nature of progress itself. If such sophisticated, hard-won knowledge was so deeply embedded in society, how could it ever be lost? The answer lies in the very human nature of its transmission. When a guild dissolves, when a master dies without an apprentice, when a society fragments or its priorities shift catastrophically, that living library can close forever. Periods of political collapse, economic upheaval, or cultural transformation could sever these chains of knowledge, leading to what we perceive as technological regression. The perfectly fitted stones of one era might be followed by the crude rubble walls of the next, not because people became less intelligent, but because the continuous thread of specialized training was broken. This realization adds a poignant weight to every ancient wall we admire. We are not just looking at stone, we are looking at the culmination of generations of learned hands, of fathers teaching sons, of masters guiding novices through 10,000 repetitions of a perfect strike. The precision is a monument to human continuity, and that leads us to a final, reflective look at the stones not as isolated enigmas, but as pieces of a much larger, interconnected human story. The Roman roads that once connected an empire slowly grew quiet, their stones reclaimed by grass and silence. In the centuries following Rome's political collapse, something profound and tangible vanished from the landscape of Western Europe. The ability to quarry, shape, and fit monumental stone on a grand scale seemed to evaporate from common knowledge. The elegant, tight joints of opus quadratum masonry gave way to rough, irregular rubble walls held together by thick mortar. This was not a matter of changing fashion, but a clear technological regression, a step backward in the practical art of working stone. It forces us to confront a difficult truth about human progress, that it is not a steady, upward line, but a fragile thread easily broken. The knowledge of how to move a mountain is not stored in a book alone. It lives in the hands of master cutters, the organization of quarries, and the economic demand that justifies such immense effort. When those conditions disappear, the knowledge can slip into the shadows for generations. Historians of technology point to a cascade of factors that severed this continuity. The fall of the Western Roman Empire shattered the political and economic unity that had supported large-scale public works. The great state-funded projects, the aqueducts, the amphitheaters, the paved roads ceased. With no demand for massive, perfectly dressed blocks, the specialized quarries that produced them were abandoned. The guilds of builders, the collegia, lost their patrons and their reason for being, scattering their members. The intricate apprenticeship system that passed down precise geometric knowledge and tool skills fractured. Furthermore, a major shift in architectural philosophy and resources occurred. In much of early medieval Europe, the focus of major construction moved from the secular to the ecclesiastical, but the new Christian basilicas often favored brick, timber, and smaller stone, materials that were more readily available and required different, less monumental skills. The social and economic engine required to produce megalithic stonework simply shut down. This creates a fascinating historical pattern, what some scholars call context-specific peak technology. A society can reach an astonishing height of proficiency in a certain craft, perfectly suited to its needs and resources, only for that specific knowledge to later fade away because the context that sustained it is gone. The comparison across regions is telling. While Western Europe experienced this regression, the architectural flame was carried forward elsewhere. In the Eastern Roman Empire, Byzantium, the sophisticated use of brick and complex mortar formulations continued, and the immense Hagia Sophia was built, a testament to an unbroken engineering tradition. Simultaneously, in the expanding Islamic world from Spain to Persia, architects and masons achieved breathtaking feats in stone and brick, developing new forms of geometry and ornamentation that pushed the craft in different but equally advanced directions. The knowledge did not vanish from the earth, it migrated and transformed, highlighting that loss is often local, not global. The evidence of this loss in Europe is written plainly in the stone itself. Compare the clean, dry-jointed walls of a Roman fortress, where blocks fit without mortar, to the thick, irregular walls of an early medieval castle. The later walls are no less impressive in their own right, often strong and formidable, but they represent a different technological solution, one that relies on bulk and binding agent rather than precision cutting. The scale of individual stone blocks also diminished dramatically. The era of moving 200-ton obelisks or 400-ton temple blocks was over. This regression makes the surviving Roman and earlier monuments appear even more miraculous to the medieval mind, and to ours. They became seen as the work of giants or a lost, superior age, because the living memory of how they were built had truly faded. This contemplation of loss does not diminish those earlier builders, it elevates them. It shows that their achievements were not inevitable, but the product of a rare and fragile alignment of knowledge, organization, and will. It also underscores why the work of experimental archaeology is so vital. By trying to replicate these methods with period-appropriate tools, researchers are not just solving puzzles, they are performing an act of recovery, reweaving a thread of human knowledge that was once broken, ensuring that the language of the stone is not forgotten again. Granite dust hangs in the air, tasting of earth and effort. In a modern quarry, a team of researchers is not using power tools. They are armed with copper saws, dolerite hammers, and bags of ordinary sand. This is experimental archaeology, a field where history is tested not in libraries, but with muscle and stone, transforming scholarly debate into tangible, measurable reality. The goal is disarmingly simple, yet profoundly difficult: to take a hypothesis about ancient methods based on tool marks and quarry scars and see if it actually works. The process begins long before the first swing. Researchers like those involved in the famous Nova pyramid building experiment start with a specific question, a testable hypothesis. For instance, can a team using only replica tools quarry, shape, and move a multi-ton block within a plausible time frame? Every variable is considered. The tools are crafted from the correct materials, copper alloyed as it was then, dolerite gathered from appropriate sources. The stone is selected for its similarity to ancient bedrock. Then the experiment begins under controlled, observed conditions. The clock is running and every detail is recorded. How many strikes does it take to detach a 1-ton block using stone mauls? How many hours of sawing with a copper blade and abrasive sand are needed to cut through a foot of granite? the data that emerges is raw and revelatory. It grounds our theories in the unyielding physics of reality. One consistent finding from such projects is the surprising efficiency of abrasion. A team from Italy's Archaeological Association demonstrated that a copper saw with quartz sand could cut a groove in hard limestone at a rate of roughly 1 centimeter per hour. That sounds slow, but it is a predictable, steady pace. With multiple teams working in shifts on a single block, the work adds up. The experiments also measure tool wear. A dolerite pounding stone might lose several centimeters of its mass in a single day of hard quarrying, explaining the vast piles of spent tool fragments found at ancient sites. Perhaps the most publicly dramatic test was the moving of a Stonehenge-sized bluestone. Researchers built a wooden sledge and a trackway of greased logs. With a team of volunteers pulling on ropes, they inched the massive stone forward, proving that the transport of these megaliths was a matter of coordinated physics, not supernatural force. The true value of this hands-on science is its ability to overturn assumptions. What seems impossibly laborious on paper can reveal a quiet, rhythmic efficiency in practice. It shows that ancient methods, born from deep material knowledge and perfected over generations, were often elegantly optimized. This empirical approach does not close the book on mystery, however. It refines our questions. When a replica tool achieves a precision that mirrors an ancient mark, we gain confidence. When it cannot, we are forced to look deeper, to consider if we have missed a step in the process, a nuance in the technique, or an ingredient in the recipe. It turns speculation into a science of doing, reminding us that the greatest insights into the past often come not from what we think, but from what we can, with our own hands, recreate. A laser's point of light traces a contour no human hand could ever feel. This is how we listen to stone today, not with a hammer, but with a beam of light, translating ancient surfaces into clouds of millions of precise digital points. Modern technology has become our most powerful new tool in this ancient investigation, not to replace the old methods, but to see them with a clarity our eyes alone could never achieve. This digital lens is revolutionizing the field, shifting our perspective from broad speculation to microscopic, data-driven certainty. The key lies in its non-invasive nature. We no longer need to risk damaging a priceless artifact to study it. Instead, digital archaeologists use tools like LiDAR, which can map an entire jungle-shrouded landscape from the air, revealing the ghostly outlines of forgotten quarries and haul roads beneath the canopy. On the ground, photogrammetry allows researchers to take hundreds of overlapping photographs of a stone surface, stitching them together into a perfect, measurable three-dimensional model. You can then zoom in on this model, rotating it in virtual space, to examine a tool mark from every conceivable angle, measuring its depth and profile with sub-millimeter accuracy. This process has led to stunning new discoveries. For instance, detailed scanning of the famous Stonehenge bluestones has allowed researchers to analyze their unique mineral fingerprints. By comparing these digital signatures to bedrock in the Welsh Preseli Hills, they could trace individual stones back to their exact quarries of origin, some over 150 miles away, with a level of precision that settles centuries of debate. The technology goes even deeper. Ground-penetrating radar can map what lies beneath the soil without a single shovel strike, revealing the subterranean layout of a quarry worksite or the foundation of a loading ramp. Portable X-ray fluorescence devices held near a stone's surface can detect faint chemical residues, identifying traces of copper from a long-vanished tool or specific abrasive sands that hint at trade networks. Perhaps one of the most powerful applications is virtual refitting. Using three-dimensional modeling software, researchers can scan a stone tool and the mark it supposedly made. They can then digitally manipulate the tool, testing its angle and motion against the mark to see if the profiles match perfectly. It is a form of digital forensics, providing empirical evidence for how a specific tool was used. This suite of technologies is not about finding a single magic answer. It is about building an overwhelming body of subtle, interconnected evidence. Drone surveys map the vast topography of a quarry, showing the logical flow of extraction. CT scanning of a tool's wooden haft reveals how it was gripped and balanced for maximum efficiency. Software algorithms can analyze the flatness of a pyramid casing stone across its entire surface, quantifying the astonishing level of precision we could previously only describe with words like incredible or perfect. This digital evidence is quietly opening entirely new chapters in our understanding. It allows us to move past the grand mysteries and into the nuanced reality of daily work. We can now see the slight variations in a worker's strike, the learning curve of an apprentice, or the repair made to a chisel's edge. The stone is beginning to speak in a vocabulary of data, and what it is telling us compels a profound and necessary shift. It asks us to re-examine not just the stones but the very stories we have built around them. A textbook timeline is a comforting map, but what happens when the ground beneath it shifts? This is the moment where physical evidence, the silent testimony of quarries and tools, stands in direct, uncomfortable contradiction to a written chronology. It is a constructive tension, a necessary friction that drives the entire engine of historical discovery forward. The implications are profound, not for tearing down established history, but for expanding our understanding of human ingenuity across a much deeper canvas of time. Sites like Gunung Padang in Indonesia present this challenge with quiet force. Here, structures built from columnar basalt, a stone worked and arranged by human hands, lie buried under layers of earth that geological analysis suggests are astonishingly ancient. The tool evidence at such a site, the very methods of quarrying and shaping, if proven to be contemporaneous with the deepest layers, would imply a sophistication in stoneworking reaching back not thousands, but potentially tens of thousands of years earlier than conventional models allow. Similarly, the hypothesis of water erosion on the Great Sphinx of Giza, proposed by geologists like Robert Schoch, does not point to a specific tool. Instead, it points to the environmental context of the quarrying itself. The argument suggests the weathering patterns on the Sphinx enclosure are consistent with prolonged, heavy rainfall, a climate condition Egypt has not experienced since the end of the last glacial period. If the quarrying of the Sphinx body from the bedrock occurred during that wet epoch, the timeline for monumental stonework in Egypt would be pushed back millennia. This is not a call for fantastical narratives, but a demonstration of the scientific process of re-evaluation in action. How do we date quarrying activity when no organic material for carbon dating is present? Archaeologists turn to the geological context. They study the sedimentation that has filled quarry trenches, analyzing the pollen and minerals within to reconstruct the climate and date the period when the trench was open. They examine tool marks under high-resolution scanners, comparing the wear patterns to tools from securely dated sites. They reassess any associated artifacts, no matter how scant, with new technologies. The goal is to build a multi-pronged, evidence-based case that either reinforces the existing timeline or convincingly argues for its revision. This process naturally meets resistance, and rightly so. Paradigm shifts in any science should be hard-won. The established model, built upon decades of peer-reviewed work, provides a stable foundation. Challenges to it must withstand extraordinary scrutiny, which is why the most compelling voices in this space are not reckless speculators, but often a mix of rogue archaeologists and cautious academics who insist on following the data wherever it leads, even into uncomfortable territory. Their work underscores that history is not a static record. but a living interpretation constantly refined by new evidence. A perfect illustration of this intellectual battleground is found not in a grand new discovery, but in a radical reinterpretation of the most studied stones on Earth, the core blocks of the Great Pyramid. Most Egyptologists maintain these limestone blocks were quarried, dressed, and lifted. However, materials scientist Joseph Davidovits proposed a different origin. He suggests the pyramids were built using a form of cast stone, a geopolymer concrete made from a slurry of soft limestone, clay, water, and a mineral activator poured into wooden formwork. The evidence he cites includes the presence of air bubbles and organic fibers in the stone, the uncanny fit of blocks that seem to mold around each other, and chemical analysis showing minerals not found in the local bedrock. His theory directly challenges the tool and quarry evidence, proposing that the primary technology was chemistry, not chisels. The debate that followed is a masterclass in evidence-based dispute. Mainstream geologists and archaeologists conducted their own analyses, countering that the bubbles and fibers are consistent with natural limestone formation. They point to the identified quarries at Tura and Giza, the tool marks found on unfinished blocks, and the overwhelming logistical evidence for a massive quarrying and transport operation. This clash is not a weakness of history, but its greatest strength. It forces both sides to sharpen their evidence, to look closer, to question assumptions. Whether Davidovits is ultimately proven right or wrong is almost secondary to the process itself. It demonstrates that every stone in every ancient wall is an open question, an invitation to look again with fresh eyes and better tools. This ongoing synthesis of what we think we know, this willingness to let physical evidence rewrite the map, is the heartbeat of real discovery. It prepares us to take all these threads of evidence, from the microscopic to the monumental, and weave them into a new, more nuanced story of how humanity first learned to shape the bones of the Earth. The scattered pieces of our investigation now assemble into a coherent, breathtaking whole. We began with a mystery, a gap between simple tools and impossible results. By following the evidence from the quarry floor to the microscopic crystal, a clear and powerful narrative emerges, one that replaces magic with method and wonder with profound respect for human ingenuity. This is not a story of a single lost secret, but of a vast and adaptable technological ecosystem. Ancient builders possessed a masterful, context-specific toolkit. They understood that different stones and different tasks demanded different solutions. The brutal percussion of dolerite hammers was for quarrying granite at Aswan. The patient abrasion of copper saws with quartz sand was for slicing precise joints. The controlled force of wooden wedges swollen with water was for splitting limestone along clean lines. The elegant physics of levers, sledges, and rollers was for moving mountains, and the invisible framework of standardized measurement, geometry, and celestial alignment was for ensuring that every block, no matter how large, found its perfect place in a grand design. This toolkit was wielded not by a disorganized mob, but by a highly stratified society of specialists, from the master planner with his knotted cords and water, level to the skilled cutter whose hands knew the grain of the stone as intimately as his own skin. The evolution of this system is written in the stone record itself. It begins in the Neolithic at places like Göbekli Tepe, with the patient pecking of flint on limestone to raise monolithic pillars. It ascends through the Bronze Age, where Egyptian engineers orchestrated the industrial-scale quarrying, transport, and dressing of millions of blocks. It reaches a zenith in classical antiquity, where Greek and Roman builders integrated every technique into a seamless, efficient workflow. Consider the construction of a Parthenon, a classical Greek temple. The process was a symphony of coordinated stages. In the quarries of Mount Pentelicus, skilled workers extracted marble blocks using channels, wedges, and levers. These rough blocks were then partially dressed at the quarry to reduce transport weight before being hauled to the Acropolis. There, teams of masons performed the final, meticulous dressing, using iron chisels and abrasives to achieve the exact dimensions and subtle curves required by the architect's precise drawings. Finally, an ingenious system of ramps, ropes, and wooden cranes lifted each heavy capital and architrave into place. Every step leveraged a deep, accumulated knowledge of materials and mechanics. This synthesized view does not demystify the past by making it mundane. It accomplishes the opposite. By revealing the tangible, replicable methods, it transforms these monuments from silent enigmas into roaring testaments to human capability. The awe shifts from a question of how could they possibly to a staggering appreciation of how they actually did. They did it with intelligence, persistence, and a generational patience that modern society can scarcely comprehend. They did it by observing the world with acute clarity, by turning simple physics into monumental force, and by encoding their understanding of the cosmos into the very angles of their stone. The true secret was not a forgotten tool or an alien blueprint. It was the human mind's relentless drive to solve problems, to collaborate on a grand scale, and to create something meant to echo through the ages. With this coherent picture of their capabilities now before us, we are left facing the stones themselves with new eyes. We see the method in the majesty. And that allows us to ask the final, most human question of all. Beyond the how, beyond the sheer logistical triumph, what did these enduring stones actually mean to the people who raised them? What story were they trying to tell, not to us but to eternity itself? A finished wall is more than an assembly of parts. It is a statement carved in the language of eternity. When we shift our gaze from the brilliant how to the profound why, the stones begin to speak of something deeper than engineering. They tell a story of the human spirit's most fundamental drives, a desire to reach beyond the fleeting moment and touch something permanent. Across cultures and millennia, this urge manifested in three powerful currents: the expression of divine belief, the demonstration of temporal power, and the forging of a collective identity. The stone itself was never just a convenient material. Its very qualities were symbolic. Granite, enduring and unyielding, was chosen for the pharaoh's tomb not because it was easy, but because it was hard, a metaphor for eternal life. The luminous white limestone casing of the pyramid reflected the sun god Ra, transforming a geometric shape into a ray of solidified light aimed at the heavens. The specific quarry a stone came from often held spiritual significance, tying a temple physically and mystically to a sacred landscape. The labor, that immense generational effort, was itself a form of meaning. For the individual worker, the act of shaping stone for a divine king or a community temple could be an act of piety, a direct contribution to cosmic order. On a societal level, the coordinated effort of thousands, fed and housed by a centralized authority, was a powerful engine of social cohesion. It transformed a population into a people with a shared, visible purpose. This fusion of method and meaning finds perhaps its purest expression centuries later in the Gothic cathedral. Here, the stone-cutting techniques we have explored, the precise geometry, the complex quarrying and lifting, all served a single, soaring theological vision. The goal was to dissolve stone into light, to create a skeletal framework of piers and vaults that could support vast windows of stained glass. Every pointed arch, every flying buttress, was a calculated risk in stone, all to achieve an interior that felt weightless, a man-made space that directed the soul and the eye irresistibly upward. The cathedral was a communal project that could take centuries, involving entire towns. The anonymous masons who carved its countless figures and leaves were not just builders, they were participants in a vast act of collective devotion, each small, perfect chisel stroke contributing to a testament of faith meant to stand until the end of time. This reflection makes the ancient builders achingly relatable. Their tools were different, but their aspirations echo our own, the need to create, to belong, to make a mark that says we were here and we mattered. The pharaoh seeking immortality, the Inca king binding his people to a living mountain, the medieval community reaching for God, all channeled their highest values into the most permanent medium they knew. The technical marvel, then, is not diminished by understanding its human motives, it is magnified. It reveals that our greatest monuments are not just triumphs of engineering, but triumphs of will. They are the physical form of a question every culture asks: what do we value enough to build in stone? With this understanding of the profound why now framing the ingenious how, we are finally prepared to look at the entire body of evidence with clear eyes. What, in the end, does all this accumulated knowledge about quarries, tools, and human ambition leave truly unexplained? Granite boxes in the Serapeum of Saqqara hold a silent, cold challenge. These are not simple sarcophagi, they are immense containers carved from single blocks of granite and basalt, each weighing over 70 tons, with interiors so smooth, corners so sharp, and surfaces so flat that they exhibit a precision we associate with modern machining. The tool marks where they exist are fine and consistent, suggesting a cutting motion of unwavering steadiness. While the abrasion theory explains much, the sheer scale and flawless execution of these boxes, deep within an underground crypt, push the boundaries of what we believe was possible with copper saws and sand. They stand as a quiet, physical question mark. Similarly, scattered across the jungles of Costa Rica lie hundreds of stone spheres, some perfectly round to within 2 millimeters. Carved from granodiorite, a hard volcanic rock, their near-ideal sphericity and varying sizes, from a few centimeters to over 2 meters in diameter, present a manufacturing puzzle. The accepted theory involves pecking and grinding with stone tools, followed by a long polishing process. Yet, the method for achieving and verifying such perfect geometry without standard measuring tools remains a topic of intense study and admiration. These are not mysteries of fantasy, but of craftsmanship that seems to operate at the very outer limit of hand skill. Then there is the sheer audacity of scale, exemplified by the 3 colossal blocks known as the trilithon in the Baalbek terrace. Each one weighs approximately 800 tons. We have discussed the 1,000-ton stone left in the quarry, but these were moved. The logistical nightmare of transporting and positioning these behemoths, even with every technique of levers, rollers, and ropes we understand, strains the imagination of even the most experienced engineers. The how is modeled, but the why, the overwhelming drive to attempt it, still resonates as a profound statement of intent. Perhaps one of the most materially puzzling anomalies is the phenomenon of vitrified stone. At a number of Iron Age hill forts in Scotland and other parts of Europe, sections of stone ramparts have been fused together into a glassy, slag-like substance. The temperatures required to melt such rock approach 1,100 degrees Celsius. Theories have ranged from deliberate construction using fire and an accelerant to the effects of massive, sustained wildfires. Yet no consensus fully explains the pattern and extent of the vitrification seen at these sites. It is a literal meltdown in the archaeological record, a thermal event frozen in time that defies a simple narrative. These outliers are not failures of the scientific method, they are its essential fuel. Researchers like geologist Robert Schoch, who investigates weathering patterns on ancient structures, or materials scientists analyzing unusual stone compositions, do not dismiss these puzzles. They treat them as legitimate data points that our current models must eventually account for. This is how knowledge grows, not by ignoring inconvenient evidence, but by allowing it to poke and prod at the edges of our understanding. The presence of these enigmas performs a vital service. It prevents intellectual complacency. If every ancient mark fit neatly into our toolbox, the conversation would end. There would be no discovery, only cataloging. Instead, these stubborn questions ensure the field of ancient technology remains dynamic, a living discipline where a new scanning technique or a fresh analysis of quarry waste can suddenly shed light on a decades-old puzzle. They are an open invitation not to wild speculation but to better science. They remind us that the past is not a puzzle to be solved once and for all, but a conversation to be continued. Each unexplained detail is a whisper from the artisans themselves, a hint that we might still have something to learn about the depth of their resourcefulness. This respectful acknowledgement of mystery does not undermine the incredible progress we have made. It honors the complexity of the human story. It ensures that the next generation of explorers, armed with new tools and new questions, will always have a frontier to pursue. The stones have given us their testimony, and now we must learn how to listen better. This entire journey through quarries and tool marks is doing more than solving old puzzles. It is actively reshaping the very methods archaeologists use to uncover the past. The investigation of ancient stonework is no longer a niche subfield. It is becoming a central pillar of a new, more holistic approach to history, one that treats every chip, every scratch, and every quarry trench as a piece of forensic evidence. The key shift is a move away from isolated specialization and toward deep, interdisciplinary collaboration. Today, an excavation team might include not just an archaeologist, but a geologist to analyze the bedrock, a materials scientist to study tool wear under a microscope, a digital surveyor to create a three-dimensional map of the site, and an experimental archaeologist who will later try to replicate the observed marks with replica tools. This convergence of expertise transforms a simple observation into a data-rich conclusion. Leading institutions are now developing new, rigorous protocols for documenting these fragile clues. Before a site is cleared or a monument undergoes conservation, teams use high-resolution photogrammetry and laser scanning to create a permanent digital record of every surface. This virtual model captures tool marks in stunning detail, preserving them long after wind, water, or even well-intentioned restoration might alter the original stone. This digital record becomes a permanent, shareable dataset, allowing researchers across the globe to examine the same evidence and contribute to the analysis. The emerging best practice is a continuous loop of observation, hypothesis, and testing. First, digital and material analysis documents the evidence. Then, experimental replication in a controlled setting tests whether a proposed tool and technique can produce an identical mark. The results feed back into the interpretation, creating a self-correcting cycle of understanding. This methodology has a direct and powerful impact on conservation. To preserve something authentically, you must first understand how it was made. Knowing that a surface was finished with a specific abrasive, for instance, informs the choice of cleaning methods, ensuring conservators do not inadvertently erase the very history they seek to save. Understanding the structural logic of dry stone masonry, how each block locks and distributes weight, is essential for any stabilization effort. Preservation becomes an act of deep respect for the original engineering. A compelling illustration of this evolving approach is the ongoing re-examination of Angkor Wat. For decades, scholars studied the temple's magnificent carvings and grand layout. Now, using ground-penetrating radar to map subsurface features, drone surveys to model the entire hydraulic landscape, and microscopic analysis of mortar and tooling, researchers are uncovering the invisible infrastructure. They are mapping the ancient quarries that supplied the sandstone, tracing the canal networks that likely transported the blocks, and identifying different construction camps based on subtle variations in masonry style. This is revealing the staggering logistics and social organization behind the monument, telling a story not just of kings and gods, but of the thousands of anonymous workers who made it possible. This forward-looking perspective promises a future where our reconstructions of ancient technological landscapes are far richer and more accurate. We will move beyond cataloging artifacts to dynamically modeling the entire chain of operation, from the moment a master cutter selected a stone in the quarry to the final placement of a carved lintel. This has profound relevance for our modern world too. It teaches us about sustainable large-scale project management, about problem solving with limited resources, and about the social frameworks that enable great collective endeavors. Ultimately, by learning to read the stone with this new forensic clarity, we are not just uncovering how things were built, we are recovering the intellectual and collaborative footprint of humanity itself. The true legacy of ancient stonework is not locked in museums, but lives in the very principles that can guide our future. Modern engineers and green architects are increasingly looking backward, not out of nostalgia, but to rediscover a philosophy of building that is inherently sustainable, durable, and profoundly efficient. This is not about copying old forms, but about understanding the core wisdom embedded in the methods. Ancient builders worked with a fundamental constraint. They had only local materials and human-scale energy. From that limitation sprang incredible innovation, a passive, low-energy approach to construction that speaks directly to our modern challenges. The lessons are not in the stones themselves, but in the logic that placed them there. Consider the simple dry stone wall, a technology found from Scotland to Peru. Without a single drop of mortar, these walls stand for centuries. Their secret is not glue but gravity and geometry. Each irregular stone is carefully selected and placed so that its weight locks with its neighbors, creating a flexible, interlocking matrix. During an earthquake, a mortared wall is rigid and prone to cracking apart. A dry stone wall, however, can shift and settle with the moving earth, then settle back into place, its very flexibility granting it immense strength. This ancient insight into seismic resilience is now being studied by structural engineers designing for climate-resilient infrastructure. Another profound principle is thermal mass. The massive stone walls of a medieval castle or a desert pueblo are not just barriers, they are thermal batteries. They absorb heat during the day, slowing the warming of the interior spaces, and then gently release that stored heat during the cool night. This passive climate control system requires zero energy to operate, a stark contrast to the energy-intensive heating and cooling of many modern glass and steel buildings. Architects specializing in sustainable design now regularly incorporate these principles, using thick, local stone or rammed earth to create structures that are naturally temperate, drastically reducing their lifelong energy footprint. The ancient commitment to precision also carries a powerful modern lesson. The Inca pursuit of the perfect seam, where blocks fit so tightly that mortar was unnecessary, was about more than aesthetics. It was about longevity. Mortar, especially early forms, is often the weakest point in a wall. It erodes with water, crumbles with freeze-thaw cycles, and eventually fails. By mastering the fit, ancient builders eliminated that point of failure, creating structures that maintain their integrity for millennia. This teaches us the value of investing in precision and quality from the outset, building things to last generations rather than decades, which is itself the most sustainable act of all. Even the organizational models hold wisdom. The orchestration of a major quarry with its specialized roles, supply chains, and waste management mirrors the complexities of a modern construction site. Studying how ancient cultures managed resource extraction, like the Romans taking stone only from specific layers of a quarry to ensure quality, encourages a modern ethic of mindful resource use, minimizing environmental impact from the very first step. Perhaps the most direct bridge from past to future is in the very chemistry of ancient materials. For decades, scientists were puzzled by Roman marine concrete. Structures like the harbor at Caesarea have survived 2,000 years of pounding salt water, while modern concrete decays in decades. Recent research led by geologists and materials scientists has uncovered the secret. The Romans used a mix of volcanic ash, lime, and seawater. This recipe triggers a slow chemical reaction over centuries, where seawater actually permeates the concrete and forms rare, interlocking minerals that fill cracks as they form. In essence, the concrete possesses a self-healing property. This discovery is now inspiring a new generation of durable, eco-friendly concrete formulas that could reduce the massive carbon footprint of modern construction. This reflection transforms our view of history. The past is not a cabinet of curiosities, but a living repository of field-tested, ingenious solutions. Our final task, then, becomes one of preservation and respect, not merely to protect old stones as monuments, but to safeguard the knowledge they embody as a vital resource for building a resilient future. The ultimate question these silent teachers ask us is a simple one. Are we building for the next fiscal year or for the next 1,000 years? Every breath of air carries a silent threat. The faint parallel striations left by a copper saw on a temple wall, the subtle polish from a stone pounder in a quarry floor, these are the fingerprints of history. Yet they are vanishing not in a dramatic collapse, but in a slow, steady fade, erased by the very human curiosity that seeks to understand them. This presents a modern, urgent conflict, a race between accessibility for education and the physical preservation of the delicate evidence itself. Conservation scientists working with organizations like UNESCO monitor a cascade of invisible dangers. The carbon dioxide and moisture from the breath of thousands of visitors can create a corrosive microclimate on a cave painting. The oils from millions of touching hands, a seemingly harmless gesture of connection, gradually dissolve the surface patina of a stone, smoothing away the very tool marks we need to study. Even the vibration from nearby traffic or the footfall of crowds can, over decades, destabilize ancient masonry and cause microfractures. Perhaps one of the most insidious threats is subsurface. In Egypt's historic quarries and monuments, rising groundwater, often linked to modern agriculture and development, is wicking up through the stone. This water carries dissolved salts. As the water evaporates at the surface, the salts crystallize inside the stone's pores. These crystals expand with tremendous force, slowly but relentlessly pushing the stone apart from within, a process called spalling that turns solid granite into a crumbling shell. The evidence is not just at famous landmarks. Consider the colossal Olmec heads of Mexico, carved from volcanic basalt. Exposed to a humid tropical climate, they face relentless biological growth, acid rain, and thermal stress from daily heating and cooling, which gradually exfoliates their surfaces, blurring those ancient Stoic faces. Or the subsurface labyrinths of Roman quarries, now threatened by modern construction pressing down above them. The response to this crisis is a new discipline of defensive preservation, a blend of cutting-edge science and profound respect. One key strategy is the creation of controlled microenvironments. This can mean enclosing a sensitive area within a glass case that maintains constant temperature and humidity, or even constructing an entire building over a site, like the protective shelters now covering sections of Pompeii. For the most fragile contexts, the solution is replication. The Lascaux cave in France stands as a definitive, though controversial, model. After discovering that the breath and introduced contaminants of visitors were causing algae and calcification to spread over the Paleolithic paintings, authorities made a radical decision. The original cave was sealed to the public entirely. A painstakingly precise replica, Lascaux II, was built nearby. This allows millions to experience the awe of the art, while the original, silent and stable, is preserved for scientific study. This concept of a non-touch replica is now applied to everything from sections of tomb walls to delicate sculptures, ensuring public engagement does not come at the cost of permanent loss. Alongside physical protection, digital archiving has become our ultimate insurance policy. Using the three-dimensional scanning and photogrammetry we discussed earlier, conservators are creating millimeter-perfect digital twins of entire sites. These are not just records, they are permanent, immutable copies. If a wall inscription is worn smooth by wind in 50 years, its exact texture and depth will remain preserved in the digital archive, available for future researchers with tools we cannot yet imagine. This is stewardship in the digital age. The call here is not to lock history away, but to be smarter about how we share it. These quarries, these tool marks, are non-renewable resources. Once a unique surface detail is lost to erosion or touch, the data it held is gone forever. Our ability to refine our understanding, to ask new questions of the old stone, depends entirely on protecting the evidence we still have. It transforms our role from passive observers to active guardians. This responsibility leads us to a final, synthesizing thought, a moment to gather all the threads of evidence we have followed and ask what ultimate picture they now form. That journey through time and stone leaves us with a profound new lens for seeing the world. We have walked the deep trenches of Aswan, felt the ghost of the dolerite hammer's rhythm, and traced the impossibly straight lines left by copper and sand. From the patient pecking at Göbekli Tepe to the orchestrated symphony of a Roman quarry, the evidence forms a clear and humbling panorama. It shows us not a single lost secret, but a vast and adaptable human intelligence, a mastery of physics and material passed from one calloused hand to the next across generations. The mystery begins to dissolve, not into disappointment, but into a deeper, more resonant awe for the sheer scale of coordinated will. The rational explanations for the how, grounded in quarry scars and tool marks, do not diminish the monuments. They elevate the people who built them. We are left not with proof of alien intervention, but with overwhelming evidence of human brilliance. Yet, a handful of stones still whisper from the edges of our understanding. The perfect spheres of Costa Rica, the vitrified ramparts in Scotland, the staggering multi-hundred-ton blocks set in place at Baalbek, these enduring enigmas perform a vital service. They are guardians against intellectual complacency. They remind us that history is not a puzzle to be solved once and for all and filed away, but a living, breathing conversation. These outliers ensure the investigation never truly ends, inviting each new generation to look closer, to ask better questions, and to approach the past with a blend of boundless wonder and disciplined critical inquiry. They are the unanswered questions that keep the story alive, compelling us to refine our science and deepen our respect. Ultimately, these structures are far more than feats of engineering. They are the physical crystallization of humanity's most enduring drives, the need to create, to belong, to reach for the divine, and to etch a mark upon the world that says we were here. The pharaoh seeking eternity, the Inca king binding his people to the mountain, the medieval community reaching for the heavens, all channeled their highest values into the most permanent medium they knew. This understanding bridges millennia, the ancient lessons in sustainability, in building with local materials and passive thermal mass, in pursuing precision for longevity over convenience, speak directly to our modern challenges. They ask us a quiet, urgent question about our own legacy. Are we building for the next fiscal year or for the next 1,000 years? If this exploration has changed how you see a pyramid, an Inca wall, or even a simple stone in a field, that transformation is the real destination. The conversation does not end here. Share your thoughts and questions in the comments below. Let us know which mystery resonates most with you. Subscribe to continue these journeys into the fabric of our shared past. Together, we keep the investigation alive, ensuring the stories written in stone are never